Hello and welcome. Over the next several presentations, we will introduce a new method for estimating unknown input using linear functional observers. Our objective is to design an unknown input observer that is simpler and more practical than the method by Hou and Muller, thereby reducing implementation complexity. Our proposed method has 4 parts. In the first part, which is this presentation, we will demonstrate a novel symbol matrix decomposition technique. This technique allows the unknown input to be expressed in its simplest form, containing only a single output measurement, its first derivatives, and a linear combination of the stack vector, which is the stack vector of the reduced order disturbance-free system. So in this form, the unknown input, we can see that beta I is a non-zero scalar. Gamma I is a scalar. Yi of t is an output measurement vector, and it is to be selected from the output measurement vector y of t. Now, if we can remember, y of t is an output measurement vector which has p output measurements. So let us first recap from talk 1, where we consider a linear system with an unknown input. And according to the metric decomposition technique by Hou and Muller, we introduce an invertible stack transformation metric T, where T is of this form, where E is an arbitrary matrix. So that is an arbitrary matrix as long as it is selected so that T is invertible. And the other invertible matrix V is of this form, where CD is the product of the output matrix C and D. And according to Hou and Muller, if the observer matching condition holds, in other words, CD is a full column and it's non-zero, then matrix P is selected arbitrarily as long as V is invertible. We obtain a reduced order disturbance-free system where the matrix I1 tilde, I bar 1, 2V, and so on are given in our previous presentation. The main thing that we can see from here is that the unknown input is expressed in this form, where y dot t is the derivative of the output measurement vector. Now, as we remarked in our previous talk, we might end it up, if P is not chosen properly or arbitrarily, we might end it up using first derivatives of all the P output measurement. Because if this matrix V1 contains all the non-zero elements, then we can see clearly from this expression, we might end it up with P output measurements where we need to take the first derivative of all of them. The other point is that to estimate this unknown input assumptively, Hou and Muller proposed to design a reduced order Lundberger observer to estimate the entire stack vector. Okay. Now, if we can express the unknown input in this simplest form, then clearly we can see that we only need first derivative of only one output measurement. And furthermore, instead of designing a reduced order stack observer to estimate the entire stack factor, we need to estimate a linear function of the stack factor. Okay, so that's the essence of what we're going to do. So accordingly, if we propose the following unknown input estimation for d of t, compare this with Hou and Muller. All right, we can see the attractive features of our approach, which is we only use first derivative of one output measurement. We design a scalar functional observer, which is known to give us a much simpler structure, reduced order, instead of design the entire, estimating the entire stack factor x1 bar of t. And as a result, you can see that we can have a much simpler unknown input observer to asymptotically estimating the unknown input. So that's what we're going to do in this topic. So let's focus on how to achieve this decomposition. And so let us recall from the previous talk. Now, in the previous talk, where we show the decomposition and we obtain an expression where we can express x2 bar of t in terms of y of t and the vector x bar 1 of t. So that's where it came from in our previous talk. Now let's have a look at that. Now in here, what we would like to do, we take it one step further. We say, all right, let us make this matrix equal to 0. Now, if that is possible, then we can simplify the expression further. The reason for that is when V1 CE, now V1 is just a submatrix of the inverse of matrix V. So V1 times C times E is an arbitrary matrix according to Hou and Muller. Here what we say is let force this matrix equal to 0. So that's the first thing we do. Now, accordingly, if this matrix is 0, then you can see clearly that we can write x bar 2 of t in terms of v1 y of t. And we can certainly obtain the derivative of x2 bar of t. And if that is the case, when we look at the reduced order system from Hou and Muller, where a tilde 1 is given by this expression. Now, because V1 CE is 0, so we got a tilde 1 simply equal to a bar 1 1, which where we have this expression here. And that bit there, for the simplicity in the notation, we call it a tilde 1 2. All right. So this equation, reduced order system, disturbance-free reduced order system is now reduced or reduced down to this expression. And this is where we force this metric equal to 0. Okay, so from Hou and Muller, if we make V1 CE equal to 0, then we obtain this reduced order disturbance-free system. The other thing is, when we look at the expression for the unknown input, which is the one that obtained from Hou and Muller method, which was from talk 1, the previous talk. As you can see, it was given by equation 10 in here, and for the sake of simplicity in notation, we let code Q1, we see this entire expression, and Q2 is this entire expression. So from Hou and Muller, we got this expression for the unknown input. And if we have VCE equal to 0, then certainly we can simplify this expression down to this expression here. And similarly, for that whole terms in the bracket, V1C equal to 0, V1C equal to 0. So all of these terms gone, we left with minus A bar 2, 1. All right, so let's summarize what happened so far. We revisit the expression from Hou and Muller, and we make V1CE equal to 0. Now, if it is possible, then we boil down to this reduced order system, and the unknown input is further simplified in this form. Right. Now, if we let that term, and we call it C of t. Now, it is actually a linear function of the stack vector. So we can write it down according to this form in here. What we aim to do next is we will find a metric V1 and a metric E, so that this expression holds true. Okay. And notice that the metric V1 is actually linked to this metric P here. P is an arbitrary metric, was chosen in Hou and Muller. Now, if we want to find metric V1 and E to satisfy this condition, then certainly that is in fact linked to finding metric V, and which is P and E. Okay. So to proceed further, let us consider the following analysis. Now, according to the assumption that the product of CD is non-zero, in other words, the observer matching condition hold, then CD is a column matrix. It has P elements. That column has P elements. And if it is non-zero, and certainly there will be at least one output measurement exists, and we call that output measurement yi of t. And that output measurement exists in such a way that when we take the role of that output measurement, that is, we can call yi of t equal to Cix of t. And if we take Ci times d, that element there should be non-zero. And we denote it as alpha I. So if this condition holds, then there exists at least more than one, or at least one output measurement such that CD times Ci times D is non-zero. Okay. Now, if that is the case, we will pick that output measurement. Now, in the case that there are many more output measurements that give us this expression, then we would have a choice. We can pick whichever output measurement that we like to decompose the unknown input into. When we look at this decomposition, the idea there is we just pick one output measurement. Now, for the purpose of practical realization, we can pick an output measurement where it is easier and cheaper to realize the differentiation or the first derivative of that output measurement. So, according to the assumption that the observer matching condition, we can confidently, we can say that this is a fact that there would exist at least one output measurement where the row output metric here corresponds to this output measurement. And when we multiply that with the unknown metric D, it gives you a non-zero element, and we call it alpha I. And let's say we pick that yi of t output measurement for the analytical expression for the non-input. Then what we do next is we're going to rearrange the output vector according to the following. So we swap, we make that output yi into the first row of this vector. And the rest of the output measurement, which is p minus 1, we put it down in here. And so it's just a matter of rearranging the output measurements. And we pick the yi output measurement and we put it in the first row. Okay. And we call this new matrix, just for the sake of simplicity, we just call it C. We just say that this is the output matrix. All right. So the next thing we do is we go into impose the following structure. Now, this is a very important bit. We're going to impose a structure on the row matrix V1. Okay, we impose that. And we make it in such a way that the first entry is non-zero. And the rest of them are basically zero. Okay, so this is the structure that we impose on the row matrix V1. Now, the reason why we do that is very clear from the following. Now, if we look at the term here, which came from the Hou and Muller decomposition, where we got that term in there. And if we impose the row matrix V1 to contain only one non-zero element, and that non-zero element corresponds to the output measurement yi of t, then clearly that becomes only one single output measurement, the derivative of only one single output measurement. And that is significant because we're able to use only first derivative of measurement yi of t only if vi takes this structure. All right, so that's the first thing, the first significance of this structure for V1. And the other bit is when we focus on the term in here, which is the expression from here. Now, if V1 CE is 0, we're left with this expression. And when we have the structure of V1 according to 3, which is this form, then that expression is in fact a scalar. That becomes a scalar because V1 has this special structure, okay? And bear in mind that A bar 22 is a scalar. It's a submetric of A bar, but because X2 bar is a single variable, so that one is just an element in there. So we can express this in terms of a single output measurement only. And so we can actually obtain this unknown input expressed in this seamless form. Now, in this seamless form, as we can see, it contains only the first derivative of the output measurement yi of t. It contains a single output measurement yi of t, and it contains a linear function of the stack vector x1 bar t. Now, this is possible based on this condition here, and also based on the imposition of the structure of the matrix V1 according to this form. All right, so that leads us to the next question. How do we find this P matrix so that we can enforce this structure? All right, now when we look back into this expression, the relationship between V1 and P, we can see that V1 is actually related to P. Now, according to Hou and Muller, P was chosen arbitrarily, but in our approach, we need to work out how we select this matrix P so that V1 takes this special structure. We forcing the structure of V1 no longer arbitrary, but it contains only one non-zero element, and that non-zero element corresponds to the output measurement yi of t. So our first question is, what is it? How do we find P? How do we achieve this structure? Now, the answer is very clear, very obvious. It's actually pretty straightforward, actually, because what we're saying here is if we chose the metric P according to this structure where P1 is just a row matrix of dimension 1 by P minus 1. And P2 is an identity matrix of dimension P minus 1. Then we can see clearly the following analytical expression for V1. And remember, when we got this assumption, Hou, in other words, the column metric is actually non-zero, and we already pick the output measurement C1 with Cy of t, and if that assumption how Ci of d is a non-zero element, then clearly the matrix CD is of the following form. Now, by the way, this can be zero or anything. We don't really care about that, because the metric itself or the condition itself is already satisfied, because this is a column metric. As long as there is an element here non-zero, we could have CRD, which is an n which is a p minus 1 column, could be any entry in there. It doesn't matter. So if we pick, or if we choose the metric P according to this structure, then we can see clearly that V is given by the following form, where CD is this column here, And because we chose P to be this form, we can see clearly that this is an invertible matrix. It's invertible because this one has a non-zero element here, and this is an identity matrix. We can easily obtain the inverse of matrix V, and it is given by this expression. All right. So the inverse of matrix V, we express it in terms of V1 and V2, and we can easily obtain that analytically, which is this expression here. Now, so from this expression, the inverse of a metric V, we can extract V1. There you go. It's actually is in the form that we want it to be. So we are able to achieve that easily by simply imposing the structure of the metric P according to the following. So we don't make it arbitrary anymore, just like in Hou and Muller, but we pick it in such a way that we can always guarantee V invertible, and we can also guarantee that metric V1 is in this special form. All right, so we conclude easily that that can be done. Okay, our first question, we can answer that easily. We can pick we can select the matrix P to be of this form. And in doing so, we obtain V1 in this form, and similarly V2 as well. All right. Now, the next question that we're going to ask is, what is E? What is the matrix E? Now remember, E is a full column rank matrix. All right, it has to have a rank of n minus 1. And it need to be found or determined so that the metric T is invertible as well. The metric T is invertible as well. Just like in here where Hou and Muller, there was no guideline on how to select metric E apart from just pick it arbitrarily as long as T is invertible. In our approach, we're going to find metric E, and we make sure that it is a full column rank metric, and it should be found so that this condition hold. Okay, and this is the one that we impose on in our development. All right, in our development, we say that to simplify the decomposition further, we just make this term equal to 0. And now we impose a metric V1 in this form. So how do we find the metric E? The answer for that is very straightforward, actually. So what happened in here is when we have V1 times C, it is actually a row, a row matrix. It's basically picking row of the output yi measurement. And so this one is a row matrix. It is non-zero. And of course, if we want to find a metric E to ensure that VC times E is 0 and full rank n minus 1, we can see that it always exists. We can always find E, metric E. All right. Now, metric E is in fact an orthogonal basis for the null space of the row V1C. A very straightforward form there. Okay. So we now know how to find metric E. It is the orthogonal basis for the null space of V1C. And of course, MATLAB, we can actually do that very easily. We come to that later on in our numerical examples. All right, so we got metric E. We guarantee that metric E is full rank of n minus 1. Now, the next natural question that we're going to ask is, can we guarantee that this transformation matrix is always invertible? Because it's very important to have that. Otherwise, we're going to be in trouble, because even when we found the metric E, we see a column, full column matrix, and it might just end up that D is a linear combination of metric E, then T might not be invertible. That would mean that the transformation, the decomposition does not work. So our natural question here is a very valid question. Is it invertible? And the good thing about it is, yes, it is always invertible. Why is that? This came from the following relationship between V1CD and V1CE. Now, if we can go back to our previous presentation, where we look at this relationship between the inverse of a metric V and metric V is an identity matrix. Remember that? And we have this relationship here. We got V1 times CD is actually 1. It's non-zero. All right. So what does it mean? It means that we already pick the output measurement, and we already ensure that the observer matching conditions. In other words, this condition hold. Because this condition hold, and because V1CE is 0, that means that D and E are independent from each other. And that means that the metric metric T is always invertible. All right. So that's a very good outcome. Now, another thing to look into this is if we have matrix C is in canonical form, what happened in here is that the output vector y of t contains the first p variables of the stack vector x of t. And this is called canonical form. By the way, we can always transform the system into this special canonical form by a very simple metric transformation. So let's say if we got C is in this canonical form, and if we pick the first output measurement and we use it for the decomposition, and if the first output measurement is selected, it needs to satisfy the matching condition. In other words, we pick C1D, in other words, Y1 of T, the first measurement. And if it's holds, this condition holds, that means that the metric D, the first element in metric D is non-zero, because the condition here tells us that it's non-zero. That means that we can write metric D in terms of this scalar, and the rest of them we don't really care. It could be zero, it doesn't matter. It's just an n-1 column. Now, if that's the case, then we can easily select metric E of the following special form. Now, when we have metric E in this form, that means we got V1 times C, which is the first element, is non-zero, and the rest of them zero, and multiplied by E, we will have V1C equal to 0. And have a look at the metric T in here. If E is this form, and D is this form, this is always invertible, and it's always full rank. Okay, so we done a very we explain a very simple metric decomposition technique. It's simple, but it's very novel, because it allows us to express the unknown input in its simplest form, where we can pick an output measurement from the P output measurement vector. And if it's in this simplified form, we only need to use the first derivative of one output measurement. We will not have the situation where we might end it up using P output measurements derivative of P output measurement. Okay, so how did we achieve this decomposition? The answer for that is we first pick an output measurement where the matching condition holds true. So in other words, we pick an output measurement yi of t from the output measurement vector, as long as this is non-zero. Now, if we have more than one output, then we have more choices. We can pick whichever output that we like to take first derivative. And that can be for practical consideration and so on. Sometimes it might be cheaper to realize a certain differentiation of a certain signal, certain sensor. And so that gives us more practicality, flexibility in there. All right, so we pick an output measurement as long as this relationship holds. And what we do is we rearrange the output measurement vector, and we put yi of t first, and the rest of them we stack in this vector here, yi of t. And so we got the new matrix C, is Ci and Cr, just for the sake of simplicity, we just simply call it C. And then we obtain the metric V, which is non-invertible, by selecting P according to this form. All right, so if it is this form, we can easily obtain the inverse of metric V. And when we obtain the inverse of metric V, we have it in this special form. And this special form allows us to express the unknown input in terms of its first derivative of only one output measurement. All right, so once we done that, we next look for metric E. We next look for metric E. And we find metric E in such a way that this V1 times C is 0. And the answer for that is metric E can be easily obtained. And we see the orthogonal basis for the null space of V1C. In the special case where metric C is of the canonical form, and if we can arrange the output measurement that we want to take the differentiation on top. In other words, we pick y1 of t and we use its first derivative. Then we can select metric E as follows. We don't need to take the null space. That is the null space, the simplest form. Okay. And so we obtain the metric E, and that's the end of it. We got metric E, we got metric P, and therefore we know how to obtain the transformation. And then we can obtain an n-1 reduced order disturbance-free system. This one is much simpler than the one by Hou and Muller, because we got I bar 1, 1. And also, by the way, that term there only contains the measurement yi of t only. The reason for that is because V1 is now of the special structure according to equation 3, which is the one in here. So even that one is a row vector, but actually it has an element equal to non-zero. So we can actually simplify our reduced order system further. Instead of writing it that way, it's actually is in terms of the output measurement yi of t. All right, and then the unknown input is in its simplest form. There you go. Where we got beta I is in fact V1 special structure, and that's basically this beta I 1 over alpha I. Alpha I is the product of Ci times D, is a scalar. And of course, it's always non-zero. It's always non-zero. That is the nature characteristic of this decomposition, by the way. And it shows us that if we want to asymptotically estimate the unknown input, then it's inevitably we need to use at least one first derivative of one output measurement. All right. Now in Hou and Muller, they might end it up using P output measurements derivatives of first derivative of P output measurements. In our approach, we only use one only. All right. And of course, certainly, this is a linear function of the stack vector x1 bar of t or x bar 1 of t. We will not estimate x bar 1t directly. But we're going to estimate this linear scalar linear function of the stack vector by designing linear functional observers. And that we will explain more later on in later videos. Okay, so in summary, in this short presentation, we show how we can do some simple novel metric decomposition technique. We can express the unknown input in its seamless form. And this form, we can always do it. We can always achieve it as long as the observer matching condition holds. This is a significant decomposition because in terms of practicality of it, we can always guarantee that we need only first derivative of one output measurement. And furthermore, we can also provide further improvement of Hou and Muller method by designing a linear functional observer instead of a stack observer. Okay, so that's the first outcome so far regarding the extension of Hou and Muller method. And we have extensively looking into the analytical aspect of the decomposition. We can guarantee that we will always have the metric V1 in this special form, and we can always guarantee that metric E is a cis, and we can always guarantee that the metric T is invertible. And we have basically a very simple algorithm, step-by-step algorithm, where we can achieve the decomposition. And this results is based on our book, the new book, which is on chapter 2, section 2.1. Now, thank you very much for watching. In the next video, which we call it topic 2, part 2, we will look at a few numerical examples. We will show using MATLAB how we can obtain the decomposition according to this expression. So we're going to look at a few numerical examples, and we will explain how we can systematically decompose and obtain the unknown input in this form. Okay, so thank you very much for watching, and I hope to see you again in the next video. Thank you. Bye for now.